All right, our day 3 lesson is on finding the feasible region and the vertices of a system of inequalities. Now, if you haven't gone through and watched the day 2 video, I would recommend doing that first because that's going to describe how we graph a system of inequalities and what that looks like. So here are the definitions for today. A feasible region is the set of possible solutions in a linear programming problem. In other words, it's the shaded area and any solid boundary lines along that shaded area. Now, a vertex or vertices, if we're talking about more than one vertex, is a corner of the feasible region where two or more boundaries meet. So the feasible region is the solution area. So all the different shaded areas that overlap, but also the solid boundary lines along that shaded area. And then the vertices are those corners. So let's take a look at a visual for you to get a better picture of this. So let's say I've got my boundary lines here on some type of problem, and I see that the overlapping shaded area is inside the middle of this quadrilateral here. So you can see it's shaded in gray. That whole area is what we call the feasible region, like feasible area. That's where all the solutions are feasible or possible for this linear programming problem. Now, the vertices are the corners, okay? Now, it's not all the corners that you see on the graph everywhere. It's only the corners along this feasible region. So when we shade just inside this shape, we see that there are 4 corners, and those corners have coordinates, the x and y coordinates that we can use to apply a name. Now, these vertices are important because these are the x and y pairs that we're going to use next week with our objective function. So remember, with our application problems, there's always a reason why we're looking for a certain combination of x and y. It might be to maximize profit, or it might be to minimize fat content, or but for the most part, you're trying to either find a maximum value or a minimum value. And those maximum and minimum overall values aren't going to come from combinations inside the feasible region. It's always going to come from one of the corners or vertices of this feasible region instead. So that's why we want to focus on finding the vertices of the feasible region. Let's actually take a moment to do a problem like this together. So this doesn't have any context to it. There's no application, but this is just a system of inequalities listed here. We're going to find the vertices of the feasible region. So to do that, we want to start by graphing the system. So we're going to use Desmos to do that. We're going to identify the feasible region based on which shaded areas overlap. And then we're going to identify the vertices of that feasible region. So let's get Desmos up here. And we're going to have to start by typing in our inequalities. So y is less than or equal to 1/2 x plus 3. We have 2x minus y is less than 6. And 2x plus 3y is greater than -6. Now let me just double check and make sure that I typed that in correctly. Okay, looks good to me. Now let's make it full screen. Okay, so if we take these and go one at a time, I don't really like to have the color black on there. It's just too dark. Let's go orange for this one because I think the others were red and blue. Yep. All right, so for this first one, the orange one, the feasible region just of that one inequality is down below. It's where our solutions are, below that boundary line. When we include the second one in red, we see it's to the upper left-hand side of that red. So what area do these two have in common? It's down here, the one that's shaded darkest in red and orange. So as of right now, that's where our solutions would be. But we have a third inequality that also says it has to be above this boundary line. So what area is shaded or overlapped by all three? It's in the middle of this triangle here. Okay, so this would be the feasible region, anything inside the triangle formed by these three boundary lines. All right, so here's my boundary lines. what I need to do is shade inside of there. So I'm going to actually use a highlighter and try to shade that as best I can. I apologize if I go outside of the boundary lines. Try to stay inside as much as possible. There we go. All right, so that's our feasible region. Notice it's anything on the inside where it's shaded, and it's also along this edge, along this side, because that's the solid boundary line. Those are solutions. Anything on this dash boundary line is not a solution. This dash boundary line is not a solution. Okay, so what we're looking for next is we are looking for the vertices. So we want to know what are the coordinates of these three corners that we have along our triangle. Sorry. One, two, three. Okay, so to find that, we're going to go back to Desmos. And remember in Desmos, you can literally just click on it to see what it looks like. So if you click on any one of these boundary lines, it's kind of going to change the shading. But it also makes those intersections appear. Notice I have a dot here, but that's not the intersection of my boundary line. So I don't really care about that. That's just my x-intercept of that line. And I got one more corner over here. All right, so those are my vertices. So I have 6, 6. I'll label that up here, 6, 6. Down here, I believe that was 1.5, -3. And I saved that third one for last because that's the hardest one. It's got all these digits. So -4.286. And we don't want to round on this. We want to give exact values, 0.857. All right, so that, of course, is that vertex. All right, so we have 3 different vertices, and we have found them using graphing technology. So that's just a basic example. And again, next week when we talk about objective functions, the maximum or minimum value that we're looking for in a linear programming problem will always happen at one of those 3 vertices. So those are the important ones. So on Monday, we talked about these application problems, and one problem we did was on Brantley's Bakery, having these constraints that we wrote together, these inequalities. So we're going to graph the system of inequalities, and then we're going to use that to sketch, just like we will on the assignment for today. So if you haven't already, you maybe want to pull up the assignment, the day 3 assignment, and then we'll go through this together. All right, to try to save a little time, I have this pre-typed in here. And we're looking for where these 4 sections or areas overlap, finding that feasible region. So kind of going one at a time, I can keep track of what area is the feasible region. And if I zoom in on this, I can see that it's going to be in between here. Okay, so I don't really care about this dot up here because that's not below this red line. So it's got to be below the red line, below the blue line, above the, I guess I'm not sure what color that line is, purple maybe, and then to the right of the green line. Okay, so it's inside this quadrilateral shape. All right, so I'm going to go back to Desmos, and we are going, excuse me, back to our lesson, and we are going to sketch by plotting our points first. Okay, so when you're in Cami, change the size of your dot to maybe like a number 6 or a number 8. And then I want to put a dot at 0, 9, 0, 0, 6, 0. So 0, 9, 0, 0, 6, 0. And then that last one was at 1, 8.333. So 1 and then 8.333 would be just a little bit above the 8. Right in there. In Cami, you have that straight line tool as well. So I would encourage you to use that rather than trying to freehand it. And all of my lines were solid, so I don't have to worry about changing that to dashed lines. There we go. And then we also fill it in. Okay, so you can just grab your pen, or in this case, I like using my highlighter. It just colors a little bit faster when it works. There we go. All right, then the last thing that we need to do is just identify what those coordinates were by listing your vertices. So we had 6, 0, 0, 0, 0, 9, and if I remember right, this was 1, 8.3 repeating on that one. All right, so that is all we need to do for the application problem. We've got the inequalities already listed. You just graph those in Desmos. We find that feasible region, click on the vertices, and then we're just transferring that over to your assignment. So just like I did, I would encourage you to plot the ordered pairs first, plot those vertices, then connect them with your lines, color it in, and make sure to list each of the vertices on that.